Hello everyone. My name is Kanchan, and today I'm going to present my project title named Air Quality Index Forecasting and Health Risk Analysis. The project in this project we connects the environmental data science and healthcare and analytics, addressing a critical real world challenge. So, what is the problem background and motivation behind this topic? As we all know that air pollution is the one of the most biggest health risk. Poor air quality increases respiratory diseases like asthma, COPD, and ARI, especially among populations. Currently monitoring system. So, what is the limitation behind current monitoring system? So current monitoring system are reactive, means they warm us after pollution peak occurs. They often lag between data recording, cause delay public responses. So our mission is to design a system that can forecast AQI, predict health impact, and alert high risk region. So next is what is AQI? AQI is air quality index. As we all know, next is objective for AQI forecasting. So in this we will forecast AQI using deep learning models, identify respiratory health risk in populations, enable early warnings for high risk areas, develop intervention strategy based on predictions, support policy making and urban planning with reliable air quality insights. What is the aim of this project is to develop a predictive system that accurately forecast air quality index level and identify high risk respiratory health areas, and and enable generating early warnings so that public can alert about the uh, respiratory conditions. So what is the flow process of this project? First, we collect the data, then we pre-process it, then we do EDA, then we will train the model, then evaluation part, and then we will deploy the model. So in the first step, we will collect the data. We use an integrated data set which combine the AQI, health, and weather data. For the features include in our dataset are CT, date, EQI, PM 2.5, PM10, NO2, SO2, CO, and O3. All these PM 2.5, PM10, NO2, SO2, CO, and O3 are our pollutants. And along with that, we also include temperature, humidity, wind speed, and rainfall, which they include in the weather data. And in the health cases, we also included the asthma cases, COPD cases, and ARI cases. Moving forward to the second step of the pre-processing. At first we will upload our data and read it. Then we will move to no, handle missing value and duplicate values. Then we will do the date and time conversion. It is very important because in as you seen in this, it is seeing that the date is 1 January 2024, but in our CSV file it is showing hashtag, so we have to uh, change the format. So this step is necessary. What are the key outcomes of the pre-processing? Is we have removed the duplicates, handle missing value, and we solve the problem of date. And now our data set is ready for feature enhancement. Next step is the feature engineering. So first we make a new feature by using AQI and temperature, which is AQI temperature ratio equals to AQI by temperature plus 1. Then we will do the feature scaling. Then we will save the process data. In the engineering process, we overall create a new feature and standardize, and we do feature engineering, and our data is ready for EDA model training. Moving forward to the fourth step, which is exploratory data analytics, which is EDA. So in this, we plotted the five graph. So our first graph is time trend analysis. So in the time trend analysis, we can see that AQI fluctuate daily. As you can see that AQI fluctuate daily. This is the data of 2000 monthly data. It fluctuate daily with variable peaks in winters. In winters, there are most very peaks, and some cities like Delhi show a higher pollution level. So, moving forward to our next graph, which is seasonal decomposition. So, in this, the AQI follow a strong monthly cycle with visible season pollution peak. As we can see that in the season, according to season, this is changing. So in now moving forward to the pollutant correlation matrices. In this PM 2.5, PM 10, as we can see that PM 2.5, PM 10, and NO2 show high correlation with AQI, which indicates that the in vehicle dominates over AQI driven. Then we can see that then in the next graph, average AQI by city, Delhi has highest among all the cities, all the 6 7 cities, which is 1.5. And and the last graph is correlation AQI versus health cases. So in this we can see that our cross correlation between AQI and health cases, it is particularly for Delhi. Means Delhi exhibit all highest average AQI among all studied cities, indicates that here we need urgent air quality management policies. Now our next step is training the model. So first we choose the model Cerimex. So what is Cerimex? Cerimex is seasonal arenema with exogenous variable. So why we use the Cerimex model for AQI forecasting? Why not other models? AQI is a time dependent variable. Current value depend on past trends. uh, it shows seasonal patterns, as we can see in previous slide, that it is higher in winter and lower in monsoon. So we can use the Arenema model, right? But we can't use this bit because we want to include the weather factor. Arenema did not allow to include the factor, so we use Cerimex. So and we can also see in it, and we and in Cerimex, we can include the seasonality, which is weekly, monthly cycle, exogenous variable, temperature, humidity, weather, wind speed, rainfall. We can study all these in Cerimex model, and in the ARIMA model we can just like simple model. Now moving forward to the next step of Sedimex model, how we use the Sedimex model. So first we first check the we first set up the data and do the feature selection step, and then move forward to the stationary check, which is ADF test. ADF stands for augmented decay Fuller test. So first we check if AQI series is stationary using ADF test. If p value is greater than 0.05, our series is non-stationary. We have to apply differentiation. So our purpose behind this is to ensure model captures stationary temporal pattern. So next we will identify arenema order. So arenema has three main components, P, D, and Q. So from now we will find out the value of PDF because they changes accordingly. So we plotted the autocorrelation, which is ACF graph, and partial autocorrelation, which is PACF. to identify P and Q. This plot help us to select how many lag value the model should consider. So in this, we can see that the highest peak is at 1 in autocorrelation, and in partial autocorrelation, it is also 1. So the value of P and Q is 1. Now move forward to the model building using Serimax model. We trained Serimax model on 80% of the data and tested on the 20%. The model integrates seasonal pattern. As it is Serimax, so it can integrate seasonal pattern and external variable like temperature, humidity. In with this in Serimax model, we also use an equation which we will study later. Next, we will move to the evolution part. So we predict AQI for the test period and compare it with the actual value. So our ME ratio is 0.68, RAS is 0.80, MAP is 50.08%. Our observe now from this we can observe that our model is successfully captured weekly seasonality and moderate pollution serves. So now move forward to the forecast visualization. So you can see that this is the AQI of 7 days. Uh, Yearly. This is yearly. So it is high in winters, low in monsoon, and we predict the AQI of late October to early January to late December. So the blue one is the train part, orange one is the actual part, and the red one is the forecast part, and the baby pink color is the correlation part. Sorry, confusion, confidence interval. So now we can see in the future AQI prediction for the next 30 days. It is also same. Uh, in this, in this the this red one is the test part, blue is the historical AQI data, and the green dots represent the future forecast, and the little light green color shows the confidence interval. So this is the future 30 days AQI forecast which our model did. So now move to the next step. Our next step is time series forecasting using LSTM. So, why we use LSTM? Air quality index data show non-linear and long-term temporal dependencies that traditional statistics model cannot fully capture. LSTM, a variant of RNN, is specially designed to remember long-term pattern and handle time-dependent sequence effectively. It ultimately learned the relationship between the pollutants concentration and meteorological variables, making it more flexible than models like Cerimex. This is a deep learning model. We use the optimizer ADAM, loss function MSC, and activation function linear. So now we will go through the steps what we did in the time series forecasting using LSTM. So we use the past 30 data of 11 features, AQI, pollutants, and weather to predict the next date AQI. So in the first step, we use the scaling. So why we use scaling here? Because LSTM is sensitive to feature magnitude. So we normalize our data using standard scale. Now, move to the second step, which is sequence generation. So we created 1,000 of 3D input sequence that is sample across 30 days, and we took the 11 feature. So our sequence will be 3D input will be the samples into 30 into 11. So this allows the model to learn the temporal dependencies. So now this is the training part. So our LSTM model has one layer LSTM layer, which is of 64 units. Dropouts is 0.2, and we have trained for 100 epoches, which early stopping to prevent overfitting. So in the batch is 32, and the validation split is 15%. Is 15%. So now move forward to the predictions and evaluation part. Our model performance is evaluated on test data using MAE, RMSE, and MAP matrices. As you can all see that the test result here. MA is 10.145, RMSC is 13.0493, MAP is 8.83%. So this result shows that the LSTM prediction closely match the real AQI trends. So here are the key insights and observations from the LSTM model forecasting. So our LSTM model successfully learned dependencies between the AQI and the meteorological variables like temperature, humidity, wind, rainfall. We also handle seasonal variations, short-term fluctuations more effectively than traditional statistical models like Arima and Cerimex. So LSTM model works more better than the Cerimex model. So what are the key takeaways? LSTM outperforms traditional models in non-linear AQI predictions. Temporal sequence learning help capture real-world pollutant dynamics, can be extended for multi-city AQI forecasting or health risk estimation. It provides a foundations for AI-based urban air quality monitoring. So what are the advantages of this? We capture non-linear and long-term dependencies in AQI data, learn hidden relationship between multiple environmental parameters. The next is perform better in unstable or irregular AQI patterns, where classical model fails, can be extended for multi-steps and multi-variable forecast. Now we will move to our next step, which is step number 6, which is hotspot detection via clustering. So in this we clustered we clustered the various regions. So in this our first step is data aggregation. So we aggregate per city matrices, which is mean AQI, variance, 95% of AQI data, average of PM 2.5, temperature and humidity. Each record now represents a summarized pollution profile of one cities. From this, we can represent the summary of pollution profile of one city. Then we do the feature scaling part. We standardize all features to ensure equal importance before clustering. So next is a clustering model. So in K-means, we divided city into 3 cluster base. K-mean is simple and interpretable. And DB scan is a detect irregular hotspot. It is used in group dense region and isolate region. Next is bridge. It is efficient and scalable algorithm. Here we can use hierarchical clustering for large data. So the from this data set, by doing these step of data aggregation and feature scaling, and after doing the clustering algorithm, we get the k-mean score 0.143. Next step is visualization of cluster. We plotted the mean AQI versus 95% AQI data to visualize city cluster. Here you can see that the clear separation observed between the low, moderate and high AQI range. Each color denotes the different pollutions hotspot group. The purple color shows that 0 and the 2 shows that a 95 percentile of AQI. The color varies in all these data. Next is hotspot ranking. So we ranking cluster based on the 95 percentile of the AQI. Cluster 2, for instance, showed extreme pollutions with greater than 250 AQI average. So what is the use of it? We can help it help in policy making, target critical cities for intermediate interventions. Suppose in Delhi, after Diwali we can before Diwali we can take the actions to stop the vehicles, uh, stop the public vehicles, large public vehicles or private vehicles. So for the cluster 0, they have high AQI, means major metropolitan hotspot. For for cluster 1, moderate AQI, transitional zones. Cluster 2, low AQI, cleaner cities with effective pollution control. The next step is step number 7th, which is health impact modeling. But in this we use the GAM model, poisons generalized addictive model. So what is the reason behind the selection? What is the reason behind it? Health data such as a number of respiratory cases are count based and follow a Poisson distribution. As we see earlier, as we can see in our data, it shows the Poisson distribution. So GAM provide flexibility to model non-linear relationship between the predictor. Example, EQI and temperature and health outcomes. It combines the interpretability like a linear model with the ability to capture complex trends like non-linear models. So in the model training and result part, it is trained using smooth terms for continuous variable, spline function, and factors terms for categorical variables, days and month. The key outputs are AIC and pseudo R square and log likelihood. Log likelihood. We can see it in the further slides. So in the health impact model part, we first merge the data. We first load and pre-process the data, and then convert date to date time and extract months and days of the week. Then we added the lag function to capture the previous day air pollution effect. Then we will merge the unscaled AQI and health data to retain true magnitude value. Then we will remove the missing values and encode categorical values. The next step is the feature selection. We selected the 6 features, 6 key predictions influencing respiratory health. And our target is total respiratory cases. So in the next step of model training, we train the GAM model on available data and achieve a good model fit. So S is the smooth spline term for continuous variable, and F is the factor term for categorical values. And we predict the end of DF prediction case GM dot predict will generate the predicted case, and then we will save the model and get the predictions. And now we have seen the 3 main outcomes: AIC, pseudo R square, and log likelihood. Now for our model, the results are of AIC is 17932.09, pseudo R square 0.1588, log likelihood minus 881.91. And in the visualization, we can see that actual versus predicted respiratory cases. So actual cases are denoted by blue color and the predicted by yellow. So we can see that the predicted cases is the medium of the actual data. This graph shows that, and it is also high in the winters and low in the monsoon. So our next and not the last, step is a risk forecasting model. Here we combine the AQI forecast and health model. AQI forecast, Cerimex, LSTM, and health model, GAM model to predict the future health risk levels. So in the AQI forecast generation, we generate AQI values for the next 7 days. And in the health impact estimation, we health cases are predicted using the trained GAM health model. In this, we uses the Monte Carlo sampling of 500 iteration, which capture the probabilistic variation in case estimates. Here the formula of the predicted cases is alpha plus beta into AQI. So our third step is alert decision logic. So as we can, it is also our part of the project where we can generate the alert. If the cases is greater than threshold, probability of cases is greater than threshold is greater than 0.7, then this ensure that alerts are raised only when high confidence in outbreak risk. So our risk forecast summary is generated for the date today's date. It is 30 November. So the predicted AQI is 290. Predicted case mean is 166. Risk level yellow. Probability cases 0.062 and alert trigger false. This is the result our model generate. In this way, use the API also to generate the live real world application. So the next step is the model evaluation step. First, we evaluate the AQI forecast. Here we get the RMSE value 39.82, MAP 33.23, MAP 36.04. And for the health model validations, for the GAM model, AC is 17932, pseudo R square is 0.598, long likelihood is minus 881, 8881.93. Here we can see that the predicted case and observable case graph of health model. Now for the back testing RMS is 48.07. And the sensitivity analysis, for sensitivity analysis, we can look up for 15 days. RMS is 11.40, 30 days 10.58, for 45 days 11.96, and for 60 days it is 9.20. Means when the days are increasing, RMSE is increasing or decreasing and then decreasing, means it follows the non-linear trend. Then we will move to the last step of our project, that is deployment. We deployed our model successfully and get the result. Here in this, I entered the city Kolkata and I have entered try to forecast the AQI for the 3 days. And here are the data for the here is the forecast summary. API forecast for Kolkata for next 3 days is average to 125.4. So here is the forecast table. Day 1, 125.09. Day 2, 125.51. Day 3, 125.69. And the health risk level is unhealthy for sensitive groups. We can run it also. So suppose we enter Delhi. Submit it. So AQI forecast for Delhi for next 3 days is 105.1. For day 1, it is 105.19. Day 2, 104.96. day 3 105.01, and the health risk level is unhealthy for sensitive group. I know this is fetching some error, but we can try our best to decrease the reduce the error and get the better forecasting, realistic forecasting. So we deploy our code. So what are the expect what is the application of the prediction model? We made the EQF prediction model. So our first is enable government policies. Here, by using the AQI prediction system, government can generate early warnings so that people can wear masks and do not use the private transport, use public transport. And next is improved hospital responses. Hospitals are also ready for the upcoming cases. If they know the AQI trends and the respiratory cases, uh, we can give the hospitals to warning that we need 30 beds for asthma patients, like that. And smart urban planning, we can plan urban planners can incorporate predictive AQI insights to design better, uh, design healthier, sustainable environment, reducing pollution exposure. And so that's all from my side. Thank you for your time. Thank you once again.